So what is the situation for this butane sphere? So that we can start going through the HACCP first and then going through the layer protection analysis. So level sensor experienced frequent failures over the last 2 years, and maintenance records indicate indicated numerous failures over the last 2 years. So we can see here that the frequency or the demand rate that is happening at this moment, it is more than once per year, or we can see that is happening very often in this case. So the accident, when it happens, that was a surprise for the operators. This was the first time that the operators had noticed this problem, because before it had never happened. So in this case, the level in the butane sphere overpressured and popped the release valve. So the level went up. Now you have a two-phase flow going out of that PSV, process safety valve, that was in the butane sphere. So the release in this case continued for 45 minutes until pumps and valves could be aligned to the pressurized sphere into another spheres with less product. So that was a manual operation that had to be done in there in order to uh, avoid those bad consequences that could have happened. So the release of the liquefied petroleum gas product in that case was not ignited. However, if the wind was blowing in a different direction and the ignition source would have been there, then that would have been a disaster situation and maybe loss of life could have happened. So we'll start going through a HACCP um, analysis that was done. So we can see here again that layer protection analysis depend on the identification of the hazards, usually done through hazard operability study. So let's see a very simple hazard operability studies for this butane sphere. So the guide word is height and the deviation with the parameter is level, right? So high level. The deviation would be guide word plus parameter high level. Then you have the team discover or start looking for what are the causes, what can cause high level in the butane sphere, causing that scenario to develop and have the PSVs a two-phase flow, which is not uh, desired. So they analyzed there and they went through what the causes. So will be loss of the level control function L1T or LT1. So that would be this one, level control 1, with the valve in here. Then we have manual outlet valve trucks not available for offloading. That would, according to the team, that will increase the level. Manual outlet valve left closed. So there's a manual outlet valve that's closed in there. Also will, according to the team, the HACCP team will create or will initiate high level, create a situation in which high level will occur in the butane sphere. Again, the manual inlet valve left open. The product rate higher than offloaded rate, leaking the internal coils, and loss of offloading pumps. So all these ones we have to take for granted that these people doing the hazard operability studies are the experts and they are the users of this installation, so they know exactly what can cause high level. And they're just coming up with their expert information and finding out what are the causes of those high levels. So here's causes from 1 to 3, and then what is the consequence? The consequence we already kind of saw there. So the potential for explosion, equipment damage, and potential for fatality. So if we start analyzing, and in this case, we're going to analyze this loop for health and safety purposes only, even though there might be also consequences with respect to um, damage of the assets and so on, or loss of production. So these are the three first causes identified, and then also they went ahead and identified possible safeguards that could have been used in order to avoid or stop the development of that scenario, in case you, for example, loss of level control function. and so on for the other initiated events too, or causes. So they found out all these safeguards in there. So now these are for causes or initiated events 4 to 6 and 7. So there were identified 7 causes and with the same consequence. In this case, potential for fatality. And there were also risk rank with the severity and the likelihood of that severity and how the risk level or the risk ranking in here. So that means that we also need a risk matrix to, or in order to come up with these numbers. I haven't shown that risk matrix before, and you will see it later on. So, and again, the safeguards that apply to those causes, for example, loss of offloading pump, the consequence would be the same, and then the safeguards that apply to that loss of offloading pump. What could prevent that scenario from developing in the unwanted event, or developing and going and having a two-phase flow and probably an ignition source and loss potential for a fatality. So how do we put this information inside SafeGuard Profiler? So SafeGuard Profiler, you have here project name, and already we went through that. So this is your project name and document title, so Butane Sphere high level example in our case, and a description with it has to include here a potential for fatality. So here this description, what describes is the hazard from the initiated event until what happens and the potential consequence that can happen in there. So if we imported this from a hazard operability study directly, then this information would be already available for us here in SafeGuard Profiler. Otherwise, we would have to type it by hand. So we have here the reference documentations. Usually, it's the PNID references or other documents that have references in there. We have the revisions. This is for follow-up later on for the person who did the layer protection analysis, and descriptions in here so that you can follow up revision numbers of each specific layer protection analysis loop or scenario. So the scenario for high level, in this case for the butane sphere, we could have in some cases more than one deviation, but in this case we only have for high level. So we have the initiated events from 1 to 7 that we saw before, and what was the worst consequences is that it is here in this case is potential for fatality, right? So very important now it is to put the consequence rating according to the risk metrics of this company, and for the letter D for long-term disability and serious for health and safety. In this case it is environment, but in reality is for us health and safety. And then we have the total frequency, which is also given by the facility owners. So after carefully analyzing the consequences, facility owners decided that they needed to have a total frequency of 1 in 10,000. So that means 10 to the minus 4. So that number is very important before we continue. So this is all this information is put in SafeGuard Profiler in the event page. And in this case, we can see that we're working on the master scenario. Later on, we'll, as I mentioned before, we have the alternate scenarios, and in this case, there will be a copy of these master scenarios that will become alternate scenarios that we can modify and without destroying this initial scenario. So we are given certain information, or this is information that we gather either by assumptions of probabilities of failure on demands, PFDs, or that in assumptions that we made with likelihoods or frequencies of initiated events, how often things happen, right? So how often the production rate is higher than offloading rate, all in a period of 1 year. So we were looking at for a window of 1 year, and then looking at how likely or how frequent things happen in that period 1 year. So, and then also we have here the protection layers. In this case, all possible protection layers with their probabilities of failures on demand. Okay. So scenario, we have the deviation, overpressure, overflow, loss of containment through the PSVs. So the layer protections that we found, or that the hazard and probability study team found, high-level interlock that closes XVC's safety implemented function 1, which is this one here. So they decided that they needed a safety implemented function, and now we're going to verify whether that safety implemented function has the correct amount of reliability, or if the performance is enough or not. And so on here are all listed all the other recognized or accepted safeguards by the hazard and probability study team. So they decided these are safeguards, right? So how do we put them inside SafeGuard Profiler? So in SafeGuard Profiler, we list all our 7 initiated events, or all our 7 causes, and this age beside it, each one of those causes means that it came from a HAZOP import. Alright, if the age was not beside it, that means that it was manually input by hitting or by clicking the add button. When you click the add button, an empty initiated cause will have its place here, and you will have to input this likelihood, and then you will have to select the safeguard that appropriately mitigate that initiated event that will try not to end up in the hazardous event. So here we can see what these numbers come from, this mitigated frequency with respect to cause number 1. So I have those 2 safeguards, or I multiply 0.125 multiplied by 0.11 multiplied by 0.01, just like it says here, and it gives me a mitigated frequency of 0.000688. That's a mitigated frequency, and I will do for each one of those initiated events, it is associated with those safeguards, and then the multiplication is done. So we will have this column here with mitigated frequencies that at the end I will add them all, and then the mitigated frequency total will be placed in here. Then later on, I have from the previous page, I define my TF number, total frequency number, that was 10 to the minus 4, or 0.0001. And then if I divide TF over MF, it will give me 3.95 10 to the minus 2, that in this case I would like to adjudicate that number will be a probability of failure on demand of an additional safeguard. So indirectly this will be or a gap. This is a risk gap equivalent to a safety implemented function with the SIL level 1 in case that I needed a safety implemented function. It is just a graphical representation again of a gap that my mitigated frequency here in gray column, here this column in gray, and this bar has to go all the way and become equal to TF. So the idea is to have the TF equals to MF, so that I can say that I achieve, or that my total frequency was met. So in this case I still have a gap with all those initiated event and likelihoods and the safeguards. So I go through all those initiated events with the safeguards and come up with their mitigated frequencies, and then I add them up all together. So mitigated frequency is 1, 2, 3 up to 7, and then I sum them. Then I have my TF over MF, and then I come up with my probability of failure on demand of as SIL1 required for a safety implemented function. So we will see what that means in this case if I used already this high interlock level that closes XV. This is supposed to be my safety implemented function that I had there before, and I can see that today this safety implemented system is not enough. I still have a gap of SIL1, so I would have to come back to this safety instrumented loop and make it better, because now today I have a gap in there. So something has to be said about having the equipment being used has to be inside its useful life. So that's the first thing that I would do instead of trying to fix this safety implemented function and improving it and leaving all the equipment in the field, which is not correct. So the right solution in this case will be to get that equipment or check that all the equipment being used is still inside their useful life of that equipment, and that its failure rate can be considered to be constant. Okay, so that was layer protection analysis and how you go through that very simply.